started. All right. So this is a totally impromptu episode of the Weekly Space Hangout. Come on, buddy. There it is. All right. Totally impromptu episode of the Weekly Space Hangout where we are in Kennedy Space Center, just outside of Cape Canaveral, obviously in a hotel room. But we're all here for the OSIRIS-REx launch, which went off without a hitch last night, and it was a glorious experience. So this is like the first time that the three of us have been in the same area together, and we thought that we would just hang out briefly. We actually canceled an episode of the Weekly Space Hangout because we didn't think it was going to come together, but clearly we were able to make it kind of work. So we thought we'd just hang out for like half an hour to let you know sort of what our experiences were with the OSIRIS-REx launch, talk to Sondy about some of the science and sort of her role on the mission, and just answer some of your questions about space and astronomy and sort of what's going to happen with the mission now that it's safely in orbit.
Safely out to Asteroid Bennu, and I brought a meteorite.
Right on. So why don't we go back briefly here, and can you just sort of set the stage, Sondy? Why on earth are we even here at Cape Canaveral? What's the point? What's going on?
Because we hate ourselves and we love 90-degree weather and we really want to suffer.
Oh, who lives like this?
Braver humans than me.
Yeah.
We're here because yesterday was the beginning of the launch window for the OSIRIS-REx spacecraft, which is going to go visit an asteroid and bring back a sample. OSIRIS-REx stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explore. Stop it!
OSIRIS-REx, yeah.
Someone thought long and hard about that acronym. So this mission has been proposed for at least 10 years, and they were proposing it to a variety of different NASA calls with the name Osiris, because Osiris has to do with this Egyptian god of life and death and origin, and because this asteroid may come hit the Earth in sometime in the 22nd century, you should tell your relevant governmental representative that they may want to spend more money on asteroid studies and possibly deflection or impact mitigation. Anyway, having a mission called OSIRIS was appropriate for studying an asteroid that we think has a very primitive composition that might be a leftover from the origin of the solar system and may have remained mostly unchanged for the last only 4.5 billion years. But at one point they decided to apply for more money for a larger mission from a larger NASA call. For you NASA planetary nerds, this is a New Frontiers mission, and these are cost capped at about $800 million. They're led by a principal investigator, and so they applied for the New Frontiers money, and they decided, we have this OSIRIS name, but it doesn't quite sound robust enough, so we're going to call it OSIRIS-REx. We're going to add on Regolith Explorer to the name, and so that's how you got the name OSIRIS-REx.
Also dinosaurs.
Dinosaurs,
right.
Because 65 million years ago, the dinosaurs didn't have a space program, much less telescopes. And look where it got those lazy lizards.
Right.
They didn't do so well. So we have a space program, we have telescopes, and maybe someday we could deal with an asteroid should we find that it is on an impact course with Earth. And so let's talk a little bit about the science behind this mission. So one of the reasons that this asteroid Bennu was selected is because Bennu, when you look at it through a telescope, when you take spectra of it, it appears very dark. And it has an albedo of about 0.05, so it's about 5% dark, where 0 being absolutely dark reflects no light, and 1 being reflects all the light that hits it. So it's this very dark object, and if you take various meteorites into lab on Earth and you take spectra of them, the ones that have very similar spectra are these carbonaceous chondrites, which mean we think they have a very similar composition to the early solar nebula, the material that all the planets in the solar system formed out of. And so I actually brought my Allende meteorite. You can see this one here.
Oh, that's cool.
And you can see Allende has these little white chunks in it. And so those little white chunks are calcium aluminum inclusions. Those are the first things to condense out of the early solar nebula. They condense, I think, several hundred Kelvin, maybe 1,000 Kelvin. And they're formed out of calcium and aluminum. And so we think that something like Bennu may have a lot of materials like calcium aluminum inclusions. I think they actually have darker rims, so they don't necessarily make the surface of Bennu light. There may be organic materials, there may be amino acids. It may have a lot of information about the material that Earth formed out of and can give us information just about where we came from as a planet And what was kind of cool last night watching the launch is you see this vapor plume following the rocket, and that is water that came to Earth from an asteroid that is being used to propel a spacecraft to an asteroid that we think may have some water in it. And some of these carbonaceous chondrite meteorites, they can be almost 10% water by mass, which is actually really cool. That's all bound up in hydrated minerals. So the target, Bennu, is one of about 700,000 asteroids that we know of, one of 14,000 near-Earth asteroids that we know of, one of about 200 asteroids that appear to be carbonaceous chondrites. It has one of like maybe a couple dozen that has an accessible orbit, or no, and then there's like I think maybe 5 that are carbonaceous chondrites. And of those 5, Bennu is the only one that has a shape model that was derived from radar data and light curves. So if we know the shape of the asteroid ahead of time, it allows for mission planning. It allows for reducing the risk of the mission if we know that we're going to sort of a sort of top-shaped asteroid rather than a dog bone-shaped asteroid, or like the Itokawa asteroid that the JAXA's mission Hayabusa 1 went to. They rolled up to this asteroid and it was sort of elongated, but they knew ahead of time from radar that it was elongated. And so if you remember when Rosetta, the European Rosetta mission, rolled up to Comet Churyumov-Gerasimenko 67P 2 years ago, they weren't expecting it to be shaped like a rubber duck. They were expecting it to be shaped more like a stress ball. And so pretty much the whole mission was designed and planned around rolling up to a stress ball, and instead they got a rubber duck, which caused some problems. So having a shape model of this asteroid ahead of time really allowed the people planning this mission to sort of know what they're getting themselves into for OSIRIS-REx. And hopefully when we get to Bennu, we can spend more time focusing on more of the science of the composition of the surface and preparing for collecting sample from the surface than spending actually figuring out the shape. Go ahead.
No, this is good. We can let you just go for hours, I think. And
I will fall over at some point.
Oh, really? Okay.
I'll need a nap, and the plug will be pulled. I'll just drain out, and you'll have to like scoop me up and take me back to my place. So there's a couple of goals with this mission. I don't know if you're monitoring the Q&A. If people
I see a whole pile of questions.
Right.
Yeah, we'll get to that in 1 second. Yeah.
So the sort of original goal for this mission was to do sampling on the asteroid. And this idea came about, I think there was a competition at Lockheed Martin. You can read about this in a variety of articles about how could you collect sample from an asteroid? And so the gravity at the surface of Bennu is actually 10 micro-Gs. It's a microgravity environment.
Right.
It's not like here on Earth where you drop this. It'll be orders of magnitude less than the strength of gravity here on Earth. And so if you want to collect something on an asteroid, you can't just go out to the asteroid and scoop it in your hand and put it in your pocket and bring it back to Earth. It doesn't work like that. We just don't really know how things work in a microgravity environment. We have some experience on the International Space Station. We have some experience in the Vomit Comet. We have some experience in suborbital flights of how things behave in microgravity. But we really don't have an intuitive sense of how particles in microgravity behave. So there have been some studies people have been doing on Vomit Comets, but you can't just scoop grains from an asteroid surface into a box, put it on your spacecraft, put it in your sample return capsule, and send it back to Earth. So someone actually came up with the idea of shooting nitrogen gas through sort of an air filter mechanism on the surface of the asteroid, and to have the gas kick up various particles into this air filter, and then they get stuck in the air filter, and then they will put that actually into the sample return capsule, and that will close up around it, and then they'll spin the spacecraft to check how the moment of inertia of the spacecraft has changed to see how much sample they've got. And if that's successful, they'll head on back to Earth. And the spacecraft can do 3 sampling attempts, but each sampling attempt can introduce risk into the whole business. So as soon as you've collected sample in the spacecraft and verified that you have sample, the OSIRIS-REx spacecraft will get out of orbit from Bennu and return to Earth in 2023 and return the sample to the Utah desert, which is kind of cool.
So the cool thing about this, right, is that this spacecraft is gone. We launched yesterday.
The Canadians have also contributed something.
One instrument, but it is going to
like
get
a tenth of the sample.
Oh, great!
It's a sweet deal for the CSA.
It's gonna go to this asteroid that is potentially dangerous in the far future. It's going to collect material from the surface and retrieve it and bring it back to Earth. And the only other place that we've gotten significant samples from is the moon, right?
Right. So pounds and pounds of...
Right.
I'm sorry, I'm using imperial units.
Yeah.
Forgive me. I forget how much material.
A couple hundred kilograms.
400 kilograms.
Yeah.
Wow.
Yeah.
Couple hundred.
So this
Yeah.
mission is going to bring back up to 70 grams.
A couple of kilograms, I thought was going
Up to 4.4 pounds.
Okay, right. Yeah, that's about 2 kilograms.
Okay, so up to about 2 kilograms if the material is the right size, if everything goes well, there'll be a ton of material. They'll bring back the most sample from an extraterrestrial source since the Apollo missions, which is a really exciting prospect. The Japanese had the Hayabusa 1 spacecraft that brought back not much material because a lot of things went wrong on that mission, but as a testament to Japanese aerospace engineering, they were really able to bring back some sample, and they were able to derive a tremendous amount of science from that sample, and people will be deriving tremendous amounts of science from the Hayabusa sample for years to come. The other thing that's really exciting about OSIRIS-REx is there are a lot of people who have a lot of experience doing extraterrestrial material curation on this mission and helping plan the mission. So every adhesive, every material that's been used to create the sample return canister, the sample return head, there's going to be samples of all those materials kept and curated so that when we have better techniques in the coming decades than we have now, we'll be able to study those materials, study the sample, see if there's been any contamination from those materials on the sample, and use that to calibrate our understanding of the return sample and those materials. One of the reasons they're using nitrogen gas is because on Earth, those samples, when they return to Earth in 2023, they're going to be kept under a nitrogen atmosphere. Okay, so that's sample return. Sample return is really cool. Even if this mission had no cameras on board, even if it was just sampling, that would be tremendous on its own because we just haven't had sample return to the Earth on this magnitude since the 1970s.
And I'm going to let you get to Yorp in a second, but Morgan, who's been so patient listening to Sondy this entire time, what is the, like this is the first time we are really going and studying an asteroid and bringing a sample back, and from a planetary science point of view, what kinds of things is this going to tell us in our understanding of the solar system?
Yeah, this is a really big deal. And it might not have been such a really big deal 25 years ago. Because 25 years ago, we thought we had a pretty good idea of how solar systems formed. We had these 4 rocky planets on the inside, we had 4 gas giants on the outside, we had this kind of halo of material all around that, and we could construct a pretty good picture of how that all came together. But then we started finding exoplanets, and we started realizing that a lot of systems out there in the galaxy look nothing like our own. We see planets several times the size of Jupiter, orbiting 10 times closer to their star than Mercury orbits to the Sun. We find systems with planets that seem to be going backwards, with planets much larger and much smaller than those we have here in our solar system. And we had to throw the whole idea about how these things come together out the window. And so now we need all the evidence we can get about how solar systems form to try to answer this much more complicated question of how do we get our system and this vast variety of other systems. And to do that, we need to go back to the source. And the only information that we can get our hands on about the actual conditions of the solar system 4.5 billion years ago when it formed is the stuff that was actually left over from that formation process. And that's what we see as the asteroids today. And we have some of that here on Earth in the form of meteorites, but all the meteorites we have, by their very nature, have been tremendously altered, because they've all come being blasted off of some object, they've come hurtling through the Earth's atmosphere, burning up partially, and then smashing down violently into the Earth. And one of those 3 parts is going to have dramatically changed the chemical composition, the physical structure, any information about the location that this object might have come from. And all of those things are really important pieces to put together to understand not only what the solar system looked like 4.5 billion years ago, but how the various pieces in the solar system were interacting. And the asteroids are our key to trying to understand all of that ancient time today.
It's awesome. And so, part of the goal with this is to really, study this object in space, to bring that sample back. But there is also sort of the movement of this as it interacts with the sun, and how we may potentially have these dangerous objects. Are you just reading the comments? Are you just like enjoying
I know.
the comments?
I'm just cracking up at you because you know I won't get out of here without.
So I'm setting you up here. Here comes your softball, Sondy, which is, can you help us understand this idea of the Yarkovsky effect? This idea that these asteroids are actually moving in more unpredictable ways than you might think, just the fact they're going around and around the sun.
All right, so we've talked about the origins aspect of origins, spectral interpretation, resource identification, security.
Just threw Bennu at him.
Explorer, and we've talked a little bit about Regolith Explorer, the touch and go sample acquisition mechanism, tag SAM. So we'll talk a little bit about security. So we've started noticing in the past couple of decades that asteroids actually deviate a little bit from their predicted orbit, depending on size. And this was actually predicted in the 1950s by a Russian aerospace engineer named Yarkovsky, who figured that satellites, because they're asymmetrical, would absorb sunlight and re-radiate heat asymmetrically, and that would cause their orbits to change. And in fact, this is the case, and this affects asteroids. But right till this point, we've only modeled this effect in asteroids because we don't necessarily know what they're shaped like. We don't know what material they're necessarily made of, and how that heats up and re-radiates heat to space. So by visiting this asteroid that we know has been affected, its orbit has been changing over the last couple of years since we've been observing it with radar and optical telescopes. We've actually seen its orbit change, and people have modeled it and show that it could be from the Yarkovsky effect. Actually visiting this asteroid with a spacecraft, seeing how the asteroid's orbit changes as we see it from the spacecraft, and actually looking at the material on the asteroid, seeing how it heats up and cools down, will actually be able to directly measure this Yarkovsky effect. What the Yarkovsky effect does is pretty much that you have little heat photons coming off the asteroid, and over millions of years this can actually act like little thrusters on the asteroid, except it's just sunlight, which is pretty benign.
Right.
But it's change in orbit, and it can cause an asteroid to, I don't know, hit a planet at some point. So most of these asteroids, they eventually, from the Yarkovsky effect, they'll hit the sun, they'll hit Jupiter, but there is some chance that this could come hit the Earth sometime in the 22nd century. I'm not worried
specifically, about it. Bennu is on a orbit that crosses Earth from time to time.
Yeah,
right?
Not that it crosses Earth. This is an important distinction.
Right.
So it crosses the Earth's orbit?
It's what we call a potentially hazardous asteroid.
Which is just a distinction, right? It's just a category.
Right, it's asteroids that come near the orbit of Earth, but they don't actually cross it. If it were to cross it, we'd call it a virtual impactor, which is a much scarier sounding name than it actually is. It just says that one day in the far future, it's possible that this asteroid could cross the orbit of Earth, which is a low probability event, and then even much lower than that the Earth could actually be there when it crosses the Earth's orbit, and then that would be a bad day for us or for our grandkids.
For now, this asteroid presents no threat to Earth, and it is very unlikely that it will hit Earth at some point. But studying this asteroid gives us a fantastic opportunity to study this Yarkovsky effect and see how it might affect other asteroids, should in the future there come a time when there may be an asteroid that might hit Earth, and we have to understand how sunlight may affect the orbit of this asteroid. It's important. So it is an important thing to study. There are a lot of dynamicists who are super stoked to study this, and this is a great natural laboratory for understanding this process, how sunlight turns the surface of asteroids into little thrusters over time. So that's sort of an exciting thing.
Yeah. And then the next step, assuming this mission is successful, is ideally to start sending human beings out into space to visit these asteroids and start to learn to work with them and potentially move their location, right?
Asteroids are stepping stones to Mars.
Yeah.
If we're going to really start putting humans out there into the solar system, we've got to do it differently than we're doing it now, because the system we have now is very inefficient in terms of having to get all this mass from here on Earth up into space. And chemical rockets are the only way to do that. They'll be the only way to do that for a long time to come, and there's only so much that they can lift. But if we could go somewhere and pick up some of that material, for example, go to an asteroid and harvest a bunch of water. Water is very important, obviously, for human life. It's also very heavy and relatively bulky to have to carry around. It's not like a gas that you can just compress into a canister. You got to bring, many gallons of water for every astronaut for every day. If we didn't have to boost all of that water up off the Earth, but we could pick it up from an asteroid gas station, for example, that would tremendously improve our capability of getting stuff up into space and then getting those humans and their equipment out elsewhere in the solar system.
So a lot of these what we call primitive asteroids, these ones with sort of the carbonaceous chondrite composition, there's one called Murchison. I think it fell in a cow field in Australia at some point. So there's a lot of interesting organics that sometimes get analyzed along with Murchison. So this is a problem. You have contamination of meteorites on Earth. We have to go to a pristine asteroid. We have to get an unaltered sample and bring it back to Earth for study. Murchison has about 10% water locked up in the minerals on it. So if you can take asteroid material out in space and vaporize it, you can get water out of it, and you can use that for drinking water. You can split it for rocket fuel. You could use it for shielding for your space habitat so you don't get fried by radiation like the Apollo astronauts did, who are dying from heart disease at distressing rates. So water in space is great, but unfortunately a lot of these carbonaceous chondrites also have a whole bunch of nasty things in them, like sulfur, mercury, cadmium, arsenic, tellurium, antimony, a bunch of just unpleasant things you really don't want in your water.
Yeah.
So someone's going to have to figure out at some point how to filter all of those nasties out of their water, out of asteroid water, but we're not quite there yet. This is why we're sending a mission like OSIRIS-REx for resource identification to see, is there water on the surface? Are there organics in the surface? Is this something that could be an asteroid like Bennu? Could it be visited in the future by future asteroid miners who are using it to establish a more sustainable human presence in space?
Here's a good piece of asteroid or meteorite trivia for you. Meteorite falls, it's named for the closest post office if it falls in the inhabited world. Elsewhere, otherwise it's named for its location.
That's why you have all these Northwest Africa meteorites.
Yeah, or Allen Hills. Those are locations on Earth. But if it landed near the Murchison post office, that's what it's named for. Anywhere in the world, if there's a postal office within some distance of it, that's where it gets its name from.
The Australian meteorites have the best names.
So let's talk a bit about the rocket launch, because that was sort of a personal experience that I tried to see the space shuttle, the second to last space shuttle launch in 2011. It came down and there was like a delay in the fuel tank, a problem with the fuel tank, and so it got pushed back a month, and so I wasn't able to see it. And so this was the very first time that I've ever seen a rocket go off, and I gave myself like a 3-day window afterwards to be able to hang out here in case there was a bit of delay, but it was so smooth yesterday. And we actually recorded, so Chad came with me on this trip, and we recorded a ton of video and great, sound, and we did a bunch of interviews. So there's an episode coming really soon where you're going to sort of see our whole adventure coming out and watching the launch and sort of our experience of it. And so hopefully you'll get a chance to kind of see what it's like to come out to NASA, to see the facilities, to see a rocket launch. It was an amazing experience. Morgan, how was it for you?
Oh, it was wonderful. This is the second rocket launch that I've been to, and they're just such visceral experiences. For me, it's such an amazing reminder of the difference between the speed of light and the speed of sound, because you watch that thing get halfway up the sky and you hear nothing. And you're like, is it working? Is it working? And then suddenly, boom, it just hits you and everything shakes as it blasts past you.
One thing, Sawyer Rosenstein is another space journalist, and he was out there on the causeway with us, and he said, if you can actually see the shockwave move across the water, and you can actually see fish jump because they're freaked out as the sound goes past.
Because the fish were jumping
they were jumping
the time before.
And so it was hard. And I wasn't even looking at fish; I was looking at the rocket. but he said, these are some of the little things that you will experience. But it was it is just this sound, and it just kind of hits you in the chest, and you just feel the rocket.
Yeah, I wasn't really hit, but you could hear the rumbling sort of increase as time went on. And there was a lot of cheering. It was really exciting. And also, Morgan and I were watching at the Banana Creek facility in the bleachers there, which is right next to the Saturn V exhibit. So we got to spend some time noodling around under the Saturn V and taking photos of the Saturn V and running into all these space people. I think an associate PI for the Mars rovers came by. I think I saw Steve Squires wearing a very nerdy shirt.
I saw him. Yeah.
I was like, who's that? Someone's like, Steve Squires. Oh, right. Yeah, I don't recognize him when he's not at a conference.
Steve Squires is the primary investigator for the Spirit and Opportunity rovers.
So that was really exciting, just to see all these space people coming by. And Morgan ran into some friends from a research program he'd done in undergrad. So it's a great atmosphere, because it's just everyone is there, and it's a reunion of sorts.
Yeah.
There were a lot of asteroid people there, and a lot of asteroid people friends.
How was your viewing position? Could you see like the bottom of the rocket all the way?
No.
No.
Were you on the roof of the VAB?
No, we were on the causeway.
Oh.
And they actually originally got us out there, and there was like a little island in between us and the rocket.
Ooh.
Yeah, and so the person from NASA was like, "Wait a minute, this view sucks." Everybody moved down, and so we all moved down the causeway until we had this beautiful view directly across the rocket.
We had a good view though. Once it lifted off, you could see it sitting on the pad.
Yeah.
And once it got off the pad,
we could
see it all the way until it disappeared from sight.
I had some friends with very large birding lenses. I think there was a 300 millimeter, 400 millimeter, 500 millimeter lens or two around, and so you could actually see the various launch pad, not the pads, but you could see the gantries, the lightning rods, so you could really sort of get the context for the site. And so then when the rocket launched, you sort of knew what you were looking at, and then it's just the light was just super bright as the engines ignited on the Centaur. It was amazing.
Yeah, and then it went up, and then sort of, you really start to see, the Atlas V, and it went up and then curved away and went downrange, which is of course what they have to do, right? They don't, rockets don't just go up; they're going
over
that
the
way.
Ocean.
Yeah, they're going sideways, 17,000 miles an hour, and to try and get into that orbit. And so the rocket starts up, and then really tilts over, and then just heads downrange.
And it was a gorgeous evening. There weren't that many clouds. There was a nice breeze. I don't think anyone in my group got bitten by mosquitoes. We'd all treated our clothes with permethrin. I was wearing long sleeves and long pants, fully expecting to be dinner for a bunch of Aegis aegypti mosquitoes. And it was quite pleasant. So you have this beautiful sky with barely any clouds on that side. And then as the vapor trail formed, you could actually see the shadow of the vapor trail on the sky behind us. And it was really fun to go onto Facebook and Twitter afterward and see all my friends' photos, and you could sort of triangulate where they were watching from based on the angle of the shadow behind the vapor trail, which I thought was super cool.
Yeah, it was really weird. So the vapor trail was dark at the bottom and then light at the top, and because it was still in the sunlight while the sun had already gone down for us, and then you could see the shadow going down behind it off to the horizon. It was a really strange. I didn't even sort of know what I was looking at, and then we sort of pieced it together. And then later on, we got back to the press area, and the trail was still up in the air, and it was sort of circled around the moon. It was a really neat view. So it was a pretty exciting experience.
I think rockets are just fascinating because they're both maybe the simplest principle in physics. Throw stuff one way, stuff goes the other way, and yet simultaneously really, really hard to build successfully, as we've seen over the years. And so you have all these engineers working very, very hard to take this very simple idea and execute it, because that simple idea is gigantic explosion. And when you throw a gigantic explosion into anything, you suddenly make it not very easy, but very, very difficult.
So one of the extra things that we got to see, I don't know if you guys got a chance to see it, but was they took us out to see the rollout from the VIF, from the vertical integration facility of the rocket, out to the launch pad. And then as we did that, we had to go past the SpaceX gantry. And this is the one that blew up about a week ago.
We saw it through someone's telephoto lens.
Yeah, no, we were close to it. And so we could see like this blackened launch gantry that was like twisted metal, and it was a mess. And you could really see that they've got a big cleanup job on their hands, to try and fix that. So that was also sort of an unexpected bonus, and we got a couple of pictures of that as well. Don't tell Elon Musk, because it's clearly a mess, and I mean it's sad. I mean that's a 6-month setback at least. So man, so any final? There's a whole pile of questions, and people want us to talk about Proxima B, and I'd love to get a chance to.
I have no comment. I have nothing to add to that conversation.
I can definitely add to the conversation if people want to talk. I don't know if you've been thinking about it at all.
I have also not been paying that much attention to it,
Okay.
but I know about it
It's a
vaguely.
planet.
Is maybe?
Maybe.
Yeah. No, it's definitely a planet around Proxima Centauri. We just don't know if it's habitable. But that's, I went on and on about that the last time we did the live streaming. So so just to kind of give people some context here, this is, of course, a totally impromptu episode of the Weekly Space Hangout because I happen to be in the same room with Morgan Rehnberg and Sondy Springmann from previous episodes of the Weekly Space Hangout.
Also, he's at a hotel
And
with better Wi-Fi than the condo we're staying at, so we're here.
Yeah. So we just thought we would just jump on and say hi to everybody.
Let's do some questions.
The whole new season of the Weekly Space Hangout starts next Friday, and we've got special guests lined up. We've got, I hope, some increase in production values. We've got some new stuff we're going to be trying to do, so it's going to be a lot of fun, and a lot of the regular journalists will be coming back to talk. So let's take some questions. I'm going to have to lean up again.
You know what we can do is we can do.
Command plus.
Make it bigger.
Yeah.
Can we not do that in the pop out?
No, you can. Usually you can.
I think.
Oh, yep. Oh, it's happening.
There you go.
It's going slowly.
Yeah. Okay. All right.
Accessible.
Whoa! You made it too big.
Sorry.
It'll get very large.
Whoa!
Oh gosh, there's lag.
Yeah, that's hilarious.
So if you do ample minus.
Yeah. Yeah, 250.
So right now the laptop is propped on a suitcase on top of a coffee table.
Yeah,
and it's
wedged with some menus.
Yeah.
Or the various room service.
So go ahead and ask some questions.
Now it's tiny.
Amino acids in space. There you go.
Space.
What? Do you want to talk about amino acids in space?
I don't know enough about amino acids in space.
So one of the big mysteries.
Morgan.
I just taught Search for Life in the Universe this summer. One of the big mysteries that we have about the origin of life is that there are something like 500 naturally occurring amino acids, and all life on Earth, from the simplest cell to you and I, use the same 23. And there's a big question. Is that because these are the only 23 amino acids that are possible for supporting life? Or is it that we're all descended from one organism, and just by dumb random chance, that organism used these 23 amino acids to build its structures, and thus we've all inherited that for billions of years? And we've kind of got to answer that question if we want to assess life elsewhere in the universe. Because if we roll up to Europa and we find life that uses the same 23 amino acids as we do, how likely is it that that's contaminated Earth life versus brand new Europan life? And understanding, well, what is the population of amino acids out there in the building blocks that eventually went into the Earth, that eventually became you and I, helps us answer that question.
John, gotta go bigger still. John 2Y92 asks, are you sad the Cassini probe is going to be terminated next year?
I am sad, but I'm also excited because if we didn't do what we're about to do, we wouldn't be able to answer a lot of questions. So we spent 12 years playing it safe, orbiting outside the rings, taking amazing pictures, and doing all sorts of great science. But there's some science that we can only do by getting up close and personal to the rings. And so far that we've ruled that out because it's just too dangerous. But now that we've sort of said YOLO and in we go, we can get in close. And the most important thing we're going to be able to do in this last year is hopefully measure the mass of the rings. And if we can measure the mass of the rings, which we don't know even to a factor of 10 right now, then we can answer some fundamental questions about Saturn, like how old are the rings? Are they 100 million years old, or 1 billion years old, or 4 billion years old? And that's stuff we've been trying to answer for a decade, very little success. But now that we're going to get up close and personal to them, we might finally be able to unlock some of those answers.
J. Cole asks, do you think we will find intelligent life in our lifetime?
I don't know. I out of scope.
You can just have an opinion.
This is a religious question.
Scope. Well, I can tell you.
Okay.
Yeah.
I want your opinion.
Sure. Well, it's a no. Moving on.
Have you seen the drivers down here?
Yeah, we're not even sure it's here on Earth. No, I went, the last video that I did, I went, I find the Fermi Paradox really compelling. And this is this idea that the universe is huge and the universe is old, and there's no reason, according to the laws of physics, why we can't travel with sufficient technology from world to world if we're willing to go really slowly. So to get to Proxima Centauri with our fastest spacecraft today, it's going to take 75,000 years. But that's not forever. That's just a very long period of time, and maybe we can make it happen faster. So what I'm saying is that in theory, intelligent aliens will have been able to send probes, self-replicating probes, to all of the stars in the entire Milky Way, and they would create more versions of themselves, and there should be monoliths on all of the worlds in, that are in the Milky Way.
So is your position then that there is no other intelligent life in the Milky Way?
That is my position, yeah.
Interesting.
Yeah, so I find this concept, the Fermi Paradox, so compelling that we don't see these monoliths, even though the universe has been here for 13.8 billion years, the Milky Way has been around for about half that, and we still don't, no alien species got around to putting, and I use monoliths as the joke from 2001, but the gist is, to leave some artifact on a world that would let the people on that world know that they were here. We know the ancient Egyptians were here by their artifacts, and we don't see these artifacts. So at the same time, I think that we are going to have a definitive answer to whether or not there is life in the universe within our lifetimes. We are building these great new telescopes. There's the James Webb Telescope and the TESS. There's going to be the TESS.
Transiting exoplanet.
Yeah, and then there's going to be whatever follows after that, and they're going to show us. They're going to help us analyze the atmosphere of these extrasolar planets that are being turned up. And all we need to do is find some kind of evidence of life in the atmosphere of one of these worlds to tell us there's life on a whole other solar system. And that technology is in our reach. So I'm hopeful that we're going to find life around other worlds, but I don't feel like we're going to find intelligent life and not communicate. But that's just my one guy's opinion, so...
Ask more OSIRIS-REx questions. I'm not an exoplanet person, people.
Europa or Titan?
As a place to live?
Just they want to know about Europa versus Titan. What do you think?
I think that if you're going to send a mission to one or the other, Titan's a much more interesting place to do it, because the interesting stuff, the ocean's right there on the surface. We can get to it today, we can go swim around in it.
Sail on
all of that good stuff. The Europa Clipper is going to go to Europa. It's going to do a lot of amazing science, but it's not going to check out the ocean. It might confirm that it's there, but that's the best we're going to be able to do, and we're looking at, decades at the earliest down the road before we can even think about getting down into that ocean. If we go to Titan, we can sample some of that. We can look for the sorts of amino acids and things that might have to exist if we were looking for life on Titan, and we can explore a whole new liquid system. We can see the rain on Titan, the lightning on Titan, storms on Titan. All of that, to me, is much more alluring than another icy body.
Titan is awesome not just because I was on the board for a sailing club for 3 years, because you could go sailing the methane seas of Titan.
Yeah.
But someone asked in the chat Billy Gordon asked, when will OSIRIS-REx arrive? OSIRIS-REx arrives at asteroid Bennu in August 2018, and it'll spend 3 years at the asteroid, mapping the asteroid, studying it, looking at the surface in a variety of wavelengths, photographing it from pretty much every angle, before finally sampling and then bringing the sample back to Earth in 2023.
It's going to be Rosetta all over again. It's going to be so exciting when the spacecraft is there and we're getting these images of the surface and it's trying to do the actual capture as well. It's just going to...
It's 2018 is going to be amazing. 2020, the sampling attempts are going to be amazing, and then when we finally get... But unlike Rosetta, where Philae is dead and Rosetta is going to crash on the surface at some point, we're actually going to get the sample to come home. We're not going to leave the spacecraft there. We're going to bring the sample back to Earth. It's going to land in the Utah desert in 2023, and then we get to analyze the sample. So the asteroid party just rocks on forever.
Yeah, and with the Rosetta, it was a 10-year mission, and this, as you said,
forever to get out there.
Yeah, forever. We forgot. someone had to remind us from the European Space Agency. But here, 2018, that's just in a couple of years. Like, that's so soon.
Someone asked what the OSIRIS-REx spacecraft is going to do after the capsule comes back to Earth. Well, that's a really interesting question, and I don't think anyone is quite planning that yet, because someone had to get that spacecraft off Earth and to sort of worry about that. But maybe you could start thinking about what would be fun for the spacecraft to do. You're going to have a spacecraft with a sampling arm, but no sampling head, and you're not going to have a sample return canister. So is there something unique you could do with a spacecraft should the unextended mission be approved? I don't think anyone is quite ready to propose that yet. Is there another asteroid you could visit? Is there something you could go poke with an arm that doesn't have a sampling head on it?
How much propellant? Like, will it be able to get away?
Absolutely
no
no
They
idea.
won't know that till they come
Yeah.
back.
You won't know about that. There's some talk. The spacecraft also wasn't necessarily designed to handle high thermal loads, so it wouldn't necessarily be an option to send it closer to the sun unless something that could be worked out. So there's a lot that we're going to learn from the OSIRIS-REx nominal mission that goes until 2023, and who knows what will happen after 2023.
Yeah. This is a good question. So Deep Pond wants to know, what is the best stuff we'll get to do in space in our lifetime? What do you think?
Wow.
In our lifetime, what cool stuff do you think we will accomplish in space?
Like we...
And I know you guys are younger than me, so like your lifetimes.
We as in like humans in space, or just space in general?
You know, like just what's coming up? Do you think, what milestones are coming up? Do you think that we're going to be able to accomplish?
That's a good question. How much taxes do you want to pay?
Well, assuming that NASA budgets are going to get cut and things, you know, like realistically, what are we looking at?
Well, I'll tell you what I'm most excited about, and that is continuing to push farther out into the solar system and to check out Uranus and Neptune. Because every time we've gone to a new world, and especially one as large as one of the outer planets, we've discovered so much we didn't know about. You know, we got to Jupiter, and we found Io and its huge volcanoes. And we found Europa, and a moon with an ocean. We got to Saturn. We found Enceladus with ice volcanoes, creating a whole ring of Saturn around it. We found Titan with an ocean of liquid methane we had no idea was there. We have only the barest understanding of what's going on around Uranus. Why is it tipped on its side? It has rings. They're extremely dark compared to those of Jupiter or Saturn.
They're asymmetrical.
What are they made of? We don't know. Neptune has this enormous moon called Triton. It's going backwards. It's going the wrong way. There's no real plausible method to get Triton where it is, looking like it does in its orbit today. How did that happen? We have even the questions we can see are huge, unanswered questions, and that's certainly, if history is any guide, just the tip of the iceberg to what's out there. And, ice giants like Uranus and Neptune, that's a totally different kind of world than the gas giants of Jupiter and Saturn. And I think as somebody who's looking forward to new exploration, that's where it's going to be. We might put humans on Mars, they're going to find amazing things. But we already have a fascinating picture of Mars from all of the rovers and landers and satellites we've put there. We have only a faint idea of what's out there beyond the orbit of Saturn. And just New Horizons flying by Pluto told us there are things out there that we never would have expected. And I expect us to find more and more of that in the next 50, 75, 100 years.
And what do you think about human exploration? I mean, if Elon Musk follows his timetable, of course he's had this recent setback, but they plan to fire off the Red Dragon capsule in the next few years to Mars and start sending humans to Mars in the middle of the next decade, which is kind of amazing to think about if that actually happens.
Yeah, I would love to see humans out there in the solar system, just from sort of a look at what we can do kind of sense. But for me, the human program is maybe not quite as exciting because it's so large, so monolithic. We have to take safety as such a paramount concern. I think that the most fascinating, the most innovative stuff is not going to happen out of the human program, but it's going to happen out of the robotic program. And I guess it's totally a question of what interests you about exploration the most. Is it going there, or is it what you see when you're there? And for me, it's what you see, and I don't care if it's my eye or a robotic eye. Yeah. I just want to see what's out there in the universe, and hopefully one day we'll be able to follow.
Yeah. Someone asked about, do you think we can get? Oh, there you go. Aristotle asked, can we get to Proxima Centauri within our lifetime? So I can answer this one quickly. So Proxima Centauri is 4.25 light years away. It would take our best spacecraft tens of thousands of years to get there right now. The only idea that's kind of plausible is this idea of sending this starshot idea where you would essentially use laser beams to accelerate really tiny light sail spacecraft to a significant fraction of the speed of light to get there. So the very best case that we could do is send these teeny tiny little chipsats to Proxima Centauri to maybe take some pictures and send some information back to us. To actually send human beings to Proxima Centauri, that is completely outside the capabilities of human beings for the foreseeable future. Let's talk in another 100 years and see if we've gotten any closer. But unless some new breakthrough in physics comes through, there's probably going to be no way that we can actually send people to Proxima Centauri within one human lifetime. Carve out an asteroid and spin it up and put a human colony in there and let it take 50,000 years to get to Proxima Centauri. Now we're talking, but that's about it right now. Good question. So Jack Kerner wants to know, are asteroids radioactive?
Well, at the beginning of the solar system, there were a lot of various isotopes of a lot of different elements, and isotopes are just elements that have different weights. They were radioactive, and sort of everyone's favorite radioactive element at the formation of the solar system was aluminum-26. And when aluminum-26 decays, it gives off a lot of heat. So as planets and asteroids were forming, the heat given off from aluminum-26 radioactive decay actually caused a lot of planets and asteroids to melt. And so that helped this process that we call differentiation, where planets melt and heavy metals sink to the cores and lighter metals rise to the surface. And so without radioactive elements in the early solar system, we wouldn't have planets as we see them today. But all these radioactive elements, they've since turned off. All of them have since decayed into their daughter products and are no longer radioactive.
Armtesh Singh wants to know, are there any precious metals found in asteroids? Morgan.
Yes, but if you were to bring them back to Earth, suddenly they might not become so precious anymore. If you could bring an asteroid's worth of platinum or gold or what have you, you'd flood the market. And so
that is not our problem.
No,
the price for platinum group metals is actually not quite yet at the point where you would drop the bottom out of the rare earth metal market.
So let me give a cool example. So the Russians, the Soviets back then, actually brought some material back from the moon from one of their lunar landers. And unlike NASA, they've been willing to sell it. And so they sold it by the milligram on the open market to bidders. And if you take the average bid price for that, and I can't remember what it was, and you multiply it by the amount of lunar material that the Apollo astronauts brought back, NASA's sitting on something like $1 trillion of moon rocks.
Right.
But you could never actually sell those moon rocks for $1 trillion. The price would crash if you tried to do that. And the same thing would be true if you brought back any of the precious metals. The things that might be the most valuable are what we were talking about before, things like water and helium or hydrogen, things that could make rocket fuel and food and energy. All of that is maybe ultimately the most precious stuff inside of asteroids.
Yeah, and you want to just keep that stuff out in space because you want like the water and a lot of that stuff that's super useful out in space. Just keep it out in space. Nimba says, I'm really sunburnt. Yes. I am not ready for this. I'm a Canadian. Come on.
Hey?
Yeah, this place is... Who lives in a place of like 35 degrees centigrade with this humidity and there's bugs in the air and they're like the air itself is trying to feast on your flesh?
Floridians?
It's not right. Sorry. And I don't understand why there's all these Canadian snowbirds come down here to live.
They come in February.
In February, yeah, okay. They don't come in the summertime.
The dean of the College of Science, the School of Science at University of Central Florida, says it's heaven on earth in February.
In February. I've been here in May, and it still was sick and wrong.
It's even quite pleasant, say, like 8 p.m.
Yeah,
but it turns out there's a lot of hours in the day between when you wake up and 8 p.m.
And, hold on, so we get back to the... it's a hibernate or something. We get back to the press area, and the van comes to pick us up, and we open up the door for what must be 30 seconds for us to get into the van and close the door. And then we're driving down the road, and my wife says, "Look up down the ceiling." And we look up, and there's about 20 mosquitoes right above me. Just like they just got into that second that we were there. It was crazy. I don't like it one bit, and I can't wait to get back to Canada.
So Jack is asking if asteroids are different closer to the sun than they are further from the sun.
Ooh.
So that's actually an interesting question, and sort of a simple model of the solar system shows that you have asteroids that, look like they've been more processed, that are hotter, that have a slightly different composition. They're more, say, stony than asteroids as you get further away from the sun that look darker, that look primitive. And you can actually see like different populations of asteroids as you get further away from the sun. But we actually see mixing amongst these populations. We see asteroids that look like they may have formed further out, closer to the sun. We see asteroids that may have formed closer to the sun, further out towards Jupiter in the asteroid belt. So if everything was a perfect solar system, which it's not, you would see sort of there's a gradient of compositions as you move away from the sun, but we don't actually see that.
But that's important information. Because
Yes.
we come back to this question of how did the solar system form? Well, one of the things we think now is that the planets probably moved around after they formed. And if they moved around, they would have stirred up a lot of this stuff. And so, like Sondy was saying, asteroids that look like they formed close to the sun maybe were stirred to a location farther away, or vice versa. And if we can map out where those populations are, we can maybe try to back out how the planets must have had to move to push this material into the places we see it today.
There's a good question about Trojan asteroids.
Yeah, what are Trojan asteroids?
Oh, I'm going to plug myself here.
All right.
I just wrote an episode of SciShow Space
Yeah.
over on the YouTube channel
Yeah.
called Trojan Asteroids, Jupiter's Prisoners.
Yeah.
Go check that out and you'll learn all about what Trojan asteroids are. But basically they're asteroids trapped between the gravity of Jupiter and the Sun, and they orbit 60 degrees ahead or 60 degrees behind the planet Jupiter. And maybe the coolest thing about them is that if Jupiter did migrate billions of years ago, it would have happened slowly enough that its Trojan asteroids would have come with it. And so the Trojan asteroids are a sample of the population or probably a sample of the population where Jupiter formed.
Yeah.
And this is why one of the 5 proposed Discovery missions for the next round of NASA missions is one to go and tour the Trojan asteroids, checking out 3 or 4 of them up close to try to get a sense of what their composition looks like compared to, for example, an asteroid like Bennu.
Yeah, and the 2 episodes ago on the Guide to Space, we covered Lagrange points and talked about the Trojans as well. So hopefully that can kind of explain why those things are trapped in the gravity well. But that's fantastic.
There was another question about if asteroids hit the sun.
Do asteroids hit the sun?
They hit the sun all the time. And sometimes we actually see comets, these sun grazer comets, through the stereo spacecraft cameras. We see them either hit the sun or just get completely dissipated before they hit the sun. So the sun is a big bully, and it does sort of some solar system cleanup on asteroids and comets that stray too close to it.
But I'm still waiting for that comet to come really close to the sun and then get really brightened up, but then also make a close pass to the Earth so that we can see this really bright, naked eye comet in the sky.
Well, stay tuned for late 2018, early 2019 comet fans, because Comet Vertinan is coming by, and it is going to be a spectacular naked eye comet.
Is this the comet that the universe owes me?
I'm not going to promise you the comet that the universe owes you. It'll be at least a very good binocular comet. It'll be spectacular. And there's another comet coming in early 2017, like February or April, that once brightened by 10 magnitudes during a pass by Earth. So it is prone to outbursts occasionally, but that was like last in the 80s.
I can't wait.
So don't hold your breath.
Things were crazier back in the 80s.
Even the okay, I'm going to take one last question, then we're going to shut down the live stream, but this is like...
Because I need a nap.
Yeah, we all need a nap.
Fraser needs aloe.
Oh, I'm okay. So Ashwin asks, if the Yarkovsky effect were found to be significant on Bennu, could you send giant mirrors to magnify the effect and deflect the course of the asteroid?
I think there are a lot of people who talk about various deflection techniques for any sort of potentially hazardous asteroid that might in the future be found to potentially have an orbit that could affect Earth. And so there's some ideas that perhaps you could use mylar or giant mirrors or paint half the asteroid white and wait for a while, or use some sort of gravity tractor, which is pretty much just put a big heavy spacecraft next to the asteroid and modify its orbit. So there are a lot of concepts out there for how to change an asteroid's orbit. None of them have been tested. None of them are funded. So
how do you like the big mirror to magnify the Yarkovsky effect?
To concentrate sunlight on
Concentrate sunlight and heat up parts and like make thrusters appear on the
I think
surface.
That sounds pretty cool.
They all require finding these asteroids long before they hit the Earth. And that's one of our bigger deficiencies now. Something like Bennu we can predict, but something like Chelyabinsk we saw a few years ago came out of nowhere, and no giant space mirror is going to be able to push it away if we don't even see it coming.
I like the jobs question.
Yeah, okay, we'll do that too. So people wanted someone to know what your actual jobs are. So, Sonny, what is your actual job?
I'm a graduate student. I'm a graduate research assistant at the University of Arizona. I'm a planetary scientist. I worked for 2 years at Arecibo Observatory in the Planetary Radar Group, and so we zapped asteroids with radar there for 2 years, and the group there was the group that had made the shape model of Bennu that you'll see all over the place.
Yeah, so you're actually working with the OSIRIS-REx mission.
Right, I was paid for the last 2 years by the OSIRIS-REx mission.
Yeah.
So anything I've said today is out there in the news. I have not said anything new.
No, you haven't given me the scoop yet. I'll keep asking them. And Morgan, what is your job?
Yeah, I'm a graduate student at the Laboratory for Atmospheric and Space Physics, which is part of the University of Colorado at Boulder, where I work on NASA's Cassini mission. So I study the rings of Saturn, and I also work with the Fisk Planetarium doing science communication. So we develop educational programs, planetarium shows, things like that, to get out the word about all the cool stuff that's going on in space.
There you go. And of course, I'm the publisher of Universe Today, and I'm the person running this YouTube channel, so that's my job now, apparently. Anyway, so thanks everyone for watching us today. Sorry we didn't get the regular episode, but I hope this was fun. We will be, like I said, we'll be back next week, and we'll have new episodes every week all the way through the fall, winter, spring, with lots of cool guests and lots of great stuff. So thanks for watching, and now I'm going to say goodbye to the stream, if I can, or it's just going to stream forever. No. Output. Stop broadcasting. Stop all.